So it's time to introduce Compulsory Task 2, which is the biggest compulsory task in this course. Before we go into the details of what the compulsory task is about, let's go through some practicalities. This is a task that you do in groups of 2 students. So you take your lab group, for example 1A, and you divide that into subgroups. So for 1A you divide it into 1A1, 1A2, 1A3, etc. You sign up for a CT2 group by using a computer, a web browser, and go to the Canvas course web and click on People and then on the tab CT2 that should appear. I as a teacher don't see exactly what you see since I'm not a student, so please help each other to find your way there. You should also sign up your group, so for example 1A1, to a supervision time slot. Link for doing that is published on the course web. Dissemination for this task is done in 2 steps. The first step is to show and discuss with teachers your preparations for the actual programming you will do. And there is a special template for that. We will look into that. And the last step is to send in a short, simplified report on your findings. Now, before sending in that report, you should do peer review, where you also exchange some results and data with the other group. And that is described in the instructions of the task. So what should you do in Compulsory Task 2? Well, you should model a multi-effect evaporator. To be more precise, an evaporator with 3 distinct evaporators. And when you have 3 different evaporators, you can have different feed patterns. Here is an example of parallel feed. Here we have forward feed, backward feed, and finally a mixed feed. And you have to look carefully in the instruction exactly which feed pattern you should be using. So what kind of process will you be simulating? Well, you're going to be simulating evaporation of black liquor. So what's black liquor? Well, if you want to make pulp out of wood chips, a very common process is the Kraft process. So you take cooking chemicals, sodium hydroxide and sodium sulfide, and you cook wood chips, and from that you get pulp. And you wash out the chemicals because you want to reuse them, and you get a weak black liquor, and that we evaporate to a heavy black liquor. So it's this evaporation step that you are going to model. So simulating a real multi-effect black liquor evaporator like this one, which is at a pulp and paper mill not far from Lund, that is of course tricky, and it's actually way beyond this course, because for one thing it's not 3, it's more, could be 7, 8, 9, and it's not often a simple feed pattern. It can be both parallel and mixed and what have you. And there are often intricate solutions to saving energy. So we will simplify there, just having 3 evaporators. And we must simplify further, because the problem here is that the viscosity of the solution is of course dependent on the temperature, but also on the concentration in a rather non-trivial way. And also the overall heat transfer coefficient, or rather the apparent overall heat transfer coefficient, that is also dependent on the temperature, because that influences the viscosity and so on, and the concentration, and yeah. So what we have done in this task is to give you some different MATLAB files, and those will mimic what happens with the enthalpy, what happens with the apparent heat transfer coefficient for different concentrations and different temperatures. And this way you can get a rather reasonable simulation. So what MATLAB files have we prepared for you? Well, the first one is exercise 5.7, Now what is exercise 5.7? If you go to the compendium, you find it as a task that you can actually solve by hand. But things you can solve by hand, you can also solve by a computer. And to solve it by a computer, you need this file exercise 5.7, but you also need the file hliquid, which calculates the enthalpy of the liquid in exercise 5.7, and you need H-saturated steam, which calculates the enthalpy of saturated steam. So what we recommend you to do is to download all these files, put them in a separate folder, open exercise 5.7 and try to run it. Exercise 5.7 has no arguments, so you should be able to just click run. And when I do that, it says, this is not found in the path of MATLAB, so let's change that folder. And we'll do that, we get the result. Okay, what you're supposed to do is to take this exercise 5.7 and reprogram it, so it now not only uses one evaporator, but 3 different evaporators. To your help, we have some other files, BPE, that calculates the boiling point elevation for black liquor, HL black liquor, which calculates the enthalpy of the black liquor at a certain temperature and concentration, H-saturated steam again you need, and K black liquor, which calculates an apparent heat transfer coefficient. You find all the instructions in the instruction file, of course. There is a CT2 classroom template that's to use when you prepare for the MATLAB programming. We will look into that file shortly. And there is a CT2 feedback form, and you're supposed to use that when you do peer feedback. And when you do peer feedback, you should actually exchange some data and results. And the report you should write is a simplified report, and it tells you in the CT2 instruction how that is simplified. So the template for classroom exercise, that's something for you to use when you prepare, and you should show this and discuss with the teacher. So the teacher marked you as passed on the preparation. And please do this carefully before you start programming, otherwise you will waste your time and our time. So write down which group you're in, what feed pattern you're supposed to be using, make a sketch, and we have helped you a bit on the next page, we will show that soon. Write down your complete nomenclature list, so all the variable and variable names you're going to use, and specify what unit you use for each and every one. You don't want to make unit errors in this task. Then write down all mass and energy balances that you will be using. Here is the sketch. Note that the feed pattern hasn't been drawn in here, and that's because, well, you have different feed patterns. Then also write down other equations you will rely on, your assumptions and approximations, and then finally what you expect to get when you run your computer simulations. So what S divided by V tot will you expect, and what is the theoretically best value for that ratio? What are the differences or similarities between different feed patterns when it comes to K values, so apparent heat transfer coefficients, and S divided by V tot, and any other thing that you think will be important? And last but not least, and this is very important, the reason why we have this exercise to a large degree, what will the effect of boiling point elevation be? So when you include boiling point elevation or ignore it in your calculations, how will that change your results?